Okay, let's do an investigation here of a particular rational function. We're going to notice that there's a characteristic here, and it's going to kind of bleed into this idea of this topic of the point of discontinuity. But we're kind of building up to that. So let's just investigate this this rational function. So the rational function we have is 3x squared minus x minus 4 all over x plus 1. So the first part is saying state the domain of this particular rational equation f at x. Rational function f at x, sorry. So this particular rational function, we have a denominator. The denominator is this x plus 1 here. And really, anytime we have a denominator with a variable in it, we have a potential for division by 0 to occur. So we could simply say, okay, well, x plus 1, that can't be 0. So we can subtract 1 on the other side. We could say, oh, okay, well, x cannot equal -1. That is the only restriction on our domain of this particular function. So we could say the domain of this function is, in set notation, x cannot equal 1, but x does belong to the set of real numbers. So that's really the only condition, is the x cannot equal 1, or sorry, -1, or we would get a division by 0 to occur. Okay, so the next question is saying to sketch the graphs for these two particular functions. I'm going to use Desmos graphing calculator to do that, and then we'll see what we're dealing with here. So it says sketch the graphs of 3x squared minus x minus 4 all over x plus 1, and then 3x minus 4. So let's go about doing that. I'm going to open up Desmos graphing calculator. Let's just jump to that. Here we go. So we're going to call this one function, we're going to call it f at x. And that's going to equal, I think we said it was 3x squared minus x, oh, I forget the last bit here. Let's go back to it. Minus 4 all over x plus 1. Okay, minus, let's get that going again, minus 4 all over x plus 1. Okay, so if you take a look, this rational function that was a quadratic divided by a linear function, it ends up just being a line, which is kind of unique. So let's define the next function here. We had g of x, and that was equal to, oh, I think it said 3x minus 4. I think I'm right on that one. So that was the second function. So I think hopefully you see right away, if I just kind of turn this off and on, you can see that these two graphs actually sit right on top of each other. Now, what's interesting is if you look at the first graph, you're like, hey, wasn't there a non-permissible value here at x equals -1 because we have this division by 0? And I'm just going to show you here. If I just take this and I go all the way to x is equal to -1, let's see if we can get it right on there, right there. Do you see that? We have, at x is equal to -1, we have this undefined. So what's happening here is this line is actually still remaining a line, but as you approach this x equals -1 from both the left and right-hand side of -1, what's happening is this graph is actually approaching a particular y value, but it's actually not approaching it at all because there's what we call a hole there. Anyhow, we'll get to that in just a little bit, but it's an interesting thing. Again, let's see, at x equals -1, just see if I can get it right on the money here. So there's nothing there, but you can see that if I'm really close to it, it looks like it's super close to -7, right? As x approaches -1, it looks like I'm getting really close to -7. Even from the other side, if I go this way, -1, see if I can get it really close. It looks like it's getting really close to y is equal to -7, but not quite there. So we have this hole. It looks like at y is equal to -7 and x is equal to -1. So those are our two graphs. They're the exact same. So I'm not going to go about sketching them there. We just compared them on Desmos. But what I want to do here is look at question C. Replace the value of x with the non-permissible value. Well, the non-permissible value that we found was x is equal to -1. What happens when we replace that? So let's replace that in our function. What do we get? 3 times -1 squared minus -1 minus 4. And then we have -1 plus 1. Now you should see right away that division by 0 is going to occur, but something else interesting happens. So let's work through the numbers here. This is going to be 3 plus 1 minus 4 over, you should see that that's 0 on the denominator, negative 1 plus 1. What we're actually getting on the numerator as well, we're getting a 0. So this 0 over 0 is occurring, which is interesting. This is actually an indication that we have another type of a non-permissible value, which is called the point of discontinuity, which is what I showed you on the graph there. If you took a look, we had something happening at negative 1 and negative 7, right? Now, we'll work through this a little bit to get to this officially, but there is something happening here. So the 0 over 0 is actually telling us something special is happening. And in this case, it's actually going to be an indication that we have this point of discontinuity. Okay, so what I want to do is algebraically demonstrate that our rational function here is equal to 3x minus 4 for all permissible values of x. So what I'm going to do here to start, I just want to take a look at this right here. And I'm going to do some algebraic manipulation to get it to look like this. Everything legit. What we're going to do to the top here of the numerator, we're going to factor this to start. So let's do that. I'm just going to take a look here. 3x squared minus x minus 4. We're going to factor this thing, and we're going to use decomposition here. So I want two numbers that multiply to negative 12, and the same two numbers that add to negative 1. What is that? That's going to be negative 4 and 3. Negative 4 and 3. So what we do here is we're going to decompose that middle term into 3x minus 4x minus 4. And then we're going to lump the first two terms and the next two terms together here. So I'm going to lump these two guys together and these two guys together. So what we get is I can factor out a 3x out of that first term, and I'm left with x plus 1. And then I can factor out a negative 4 out of that second grouping, and then I'm left with x plus 1 again. And then I can go one step farther and factor out that x plus 1, and I'm left with 3x minus 4. Okay, so we factored that numerator. So I'm just going to rewrite that rational equation, or sorry, that rational function here as x plus 1 and 3x minus 4 all over x plus 1. And I hope you can see right away these x plus 1 terms, yeah, they divide out, and we're just left with 3x plus 4, which is what we were trying to validate, which is the case. We took this rational function that looked pretty complicated. It was a quadratic divided by a linear factor. We factored it, kind of dumbed it down, and now it's really just represented by this line. But it's not just a line. This line has that special characteristic that we kind of talked about earlier. That special characteristic was that hole. Okay, so the next question is asking, it says, explain whether the graph of y is equal to that rational function that we were dealing with has a vertical asymptote at the non-permissible value or a point of discontinuity. Well, because we have this particular relationship, and because we had this 0 over 0, or because it was dumbed down to, let's just rewrite this, because we looked at it like this and we got it to dumb down to 3x minus 4, and that non-permissible value that's typically there in the denominator disappeared, that x plus 1 in the denominator is no longer represented when we look at it in terms of this line, but there still is something happening there. We actually do not have this vertical asymptote occurring. We do have the second idea, and it's this point of discontinuity here. This point of discontinuity is occurring at x is equal to negative 1. Just because that factor in the denominator is not present in this linear statement of 3x minus 4 does not mean nothing is happening at x equals minus 1. Something is happening in the step before. It showed us that. So because we have something happening at x equals minus 1, and I showed you earlier it's at a coordinate of x equals minus 1, what is the function actually approaching? What is f at x approaching here, the y value? Well, we can figure that out. Again, we have our 3x minus 4 is what we dumbed it down to. Well, what if we put in that negative 1 non-permissible value into that equation? What do we get? So let's work that out. We're going to get y is equal to negative 3 minus 4, which is negative 7. So at negative 1 and negative 7, we have this point of discontinuity occurring. It doesn't actually equal that value. That's what the hole exists. It actually is approaching infinity as we surround -1 from the left and right. It's not ever going to equal -7. It's going to approach -7. Never equal, though. It's like an asymptote. It's never going to cross that bound. It's going to infinitely approach it.